Alright, in this video we will be looking at compressible flow, and we're going to break this up into a couple of different topics. We'll not do as complete a coverage as in the book, so I do recommend reading that also. We're going to start in section 912, and they call this compressible flow preliminaries. Basically what we have is we're going to define some new terminology, we'll take a few concepts out of fluid mechanics, blend in what we know about thermo at this point, and use this to analyze compressible flow of gases primarily. And by compressible we mean that the density changes due to the pressure changes or temperature changes. Now we're going to have a reference state for this. So like we did when we did the dead state in exergy, we're going to have what's called a stagnation state. And so this is bringing the material to zero velocity, but we're going to do it through a reversible and adiabatic process. So we're going to have an isentropic process as we do this. So if I do that, then applying the first law across a nozzle or Joule-Thomson valve or any of those kinds of devices where I have no work or heat transfer, I end up with H naught, the stagnation enthalpy, is the original enthalpy plus the kinetic energy it originally had. Again, the final kinetic energy is 0. Now once I have H naught, this stagnation enthalpy, then I can calculate T naught using, well, whatever rules you're using. If you're going to be using the ideal gas tables, or if you're going to calculate it from C sub V or C sub P, excuse me, delta T, however you're doing that. And then we're going to get P naught using the isentropic rules. So if we're using air, we can use the tables with P sub R. Otherwise, we'll have to use the rules that we had for ratios of P to the K power, or K minus 1 power. And so you'll need to choose the appropriate technique for the substance that you have. Now, one of the things that we need to do is talk about momentum. So fluid mechanics, we learn about momentum balances. Now we're only doing steady state systems, so the sum of the forces will be the change in momentum. Momentum is mass flow rate times velocity. And so if I have a simple system with one stream in, one stream out, the mass flow rate has to be same inlet to exit because of steady state, no mass change. And so I end up with the mass flow rate is constant, and the forces are going to be the change in momentum, so mass flow rate times change in velocity. And those forces are going to be either due to whatever reaction forces are holding my object in place or due to pressure on the surface. So now let's look at a gas. We've got here like a piston and cylinder, and we're just going to pump that little piston just slightly. That's going to change the pressure. It's going to just start that stuff moving. And what's going to happen is a little bitty wave will form, and it will move across the fluid. Now if you're standing still, the wave goes past you and it looks like the fluid then is moving the other direction. Okay? So if I do a little material balance over this tiny little region here, just the front of that wave there, the velocity is going to be the speed of the wave on one side and the speed of the wave with some change, okay, delta V on the other side. Now my mass in is the same as the mass out. If the mass is rho A times the speed, velocity, well, if I've defined it C, the speed that this wave is moving through there, okay, on one side it's going to be dV or delta V less on the other side, but the density will have increased because it's been squished together. Okay, so the molecules are closer together, so the density increases, the speed decreases. And if you go through and multiply this out, rho AC, rho A dV, AC d rho, AC d rho dV. The rho ACs are going to cancel. I'm left with these terms here. But compared to these, okay, I have a number that has a reasonable size times a teeny number, minus a number with a reasonable size times a teeny number here, because this is a teeny little wave. Those are equal to two teeny numbers multiplied together. Okay, tiny times tiny is really tiny, correct? So let's just call it 0. Compared to this side, it's very, very small. It's 0. And so I could use this to solve for the speed of that sound wave as it propagates through the fluid. Okay? And so I get that it's the density times the change in the speed or velocity with respect to density. Now, okay, let's do this slightly different way. My forces are pressure times area, and my momentum again, rho a v. Okay, so the difference in those, so I end up with these little terms here. So my rho a v is my mass times my velocity, so I'm getting my velocity squared now. And so my forces equal to my momentum difference. If I do some rearranging, and I'm not doing the algebra today, I can end up with this expression, okay? It's just this equal to this, rearranged. And if I take what I just said a moment ago about what C is equal to, I end up with this. C is the square root of the derivative of pressure with respect to density. Okay? Now this is generally true, and I can apply this in any case that I wish to. Okay? This is how fast a sound wave will change with pressure and density. But most of the time when I'm wanting to apply this, I'm really only caring about ideal gases, and mostly air. Okay? So rate of heat transfer is nearly 0, movement of the wave, if we assume it's fairly reversible, which it can be, we know that sound waves bounce off of walls and echo back, right? So that's an indicator that they're fairly reversible. The process in that case, reversible and adiabatic, it's isentropic. And for an ideal gas, we've already said in an earlier portion of the course that pressure times volume to the K power is a constant, where that K is C sub P over C sub V. So if I take that constant and bring the V to the K over on this side, so I divide by V to the K, well, specific volume is density. And frankly, here, since I'm talking about speeds all the time, density is better to work with than specific volume. I end up with constant times density to the K power, which is the same as dividing by specific volume to the K power. Now, if I actually do that derivative here, going through the steps, I end up with its Kp divided by the density, or Kp times the specific volume. But P times specific volume is RT, because I said it was an ideal gas. And so therefore, C for a sound wave moving through an ideal gas, for instance moving through the air, is the square root of KRT. K is C sub P over C sub V. It varies a little bit with temperature. That variation is in the back of your book. You can actually look that up in the textbook. And R is the ideal gas constant, and T is going to be the temperature. And I just need to make sure I'm using temperatures that are absolute when I do this. So let's look at an example, okay? So we'll say it's a nice 70-degree Fahrenheit day and lightning strikes 2 miles away. So how long before you will hear the thunder? So I'm talking about the speed of sound. So K, if you look that up, it's about 1.4. R is 1545 in the engineering units. Foot-pounds force per pound mole degree R. Of course, pound moles are awkward, so 28.97 is the molecular mass. So that's pound mass per pound mole. The temperature is 530 in degrees Rankine. And then I need to, of course, convert my unit. So this is G sub C, the conversion factor to get from pounds force to pounds mass. And if I do that, I'm left with just the units of foot squared per second squared. When I take the square root, that'll be feet per second. So I end up that it's taking 1,129 feet per second. Now that distance is about 2 miles, so 5,280 feet per mile times my 2 miles, divide by the speed, and it's going to take a little less than 10 seconds. But if I do the calculation of how long I see it, using the same sort of distance divided by speed, the speed of light is 9.8 times 10 to the 8th feet per second. So I'm going to see that in like less than, 1 times 10 to the minus 5th seconds. So I see it, and then it's nearly 10 seconds before I hear it. I also want to define the Mach number. Okay? Now the Mach number, I think most people have heard of it. It's the velocity something is traveling divided by the speed of sound. And you'll have to calculate the speed of sound on a case-by-case basis. But if I do that, it's very simple to take this ratio. It's going to be a unitless number. And when I get a value, if it's less than 1, I'm going to say that my flow is subsonic. If it's exactly equal to 1, it's sonic. And if it's greater than 1, it's supersonic. Now sometimes it's a lot greater than 1, which we'll call hypersonic. Usually by a lot greater, I mean on the order of a magnitude larger. So instead of being like 1, it's like 10. Okay? If it's very near 1, we'll call it transonic. Okay? So at that point, we've completed section 912. When we come back, we'll talk about how we design nozzles for flow that's going to be subsonic, supersonic, or very near there. So that completes this video.